protons and electrons, and then there is this nucleus which has protons and neutrons. So the nucleus is positively charged, and then you have electrons orbiting around the nucleus. So this is the model, Rutherford's model. To derive this, we are going to assume a hydrogen-like atom, meaning it's either hydrogen or hydrogen-like atom, meaning that there is only one electron in the one electron in the whole atom, which is orbiting the nucleus. The reason is this. For example, okay, you have an atom like this. Okay, so you have the nucleus here, and then you have electron going around it. Okay, so there is this electron. Okay. So, and this is nucleus. So the positive, this is negatively charged, minus. Okay, and here this is going to be plus Z into E. So because Z is the atomic number, it's the number of protons in the nucleus. So this is about, and E is the charge of the proton. So Z is the total charge in the nucleus. So you have E here, and then you have ZE here. Okay, and when we do this derivation, as I told you, that we would assume that there is only one electron present here. The reason is that if there is only one electron, then it is easier for me to calculate the force on it. The force on this electron is simply the force due to the nucleus only. So the force on the electron now can be written as K into ZE into E by R squared. So K, K is 1 by 4 pi epsilon naught. I am just going to keep it as K for the time being. Okay, so this is the force on the electron. Supposing that there were other electrons in this atom, then what will happen is that this is not the only force acting on the electron. The electron will be affected by the force due to other electrons. So the force of the electron will not remain just this, it will be something else. Okay, that is the reason we are not considering an atom that has more than one electron orbiting around its nucleus. So that is why we say we take either hydrogen, where you have only one electron orbiting one proton, or you have helium, which has two protons, but then you are going to ionize it. You will remove one electron from helium, so you will get only one electron left orbiting the nucleus. So that's a positive helium ion. So that is what you will have there. Okay. Or lithium. Lithium, in the case of lithium, like the atomic number is 3. So you have 3 protons in the nucleus, but then you are going to have only one electron orbiting around it, which means that you will remove 2 electrons from the atom. So you get 2 plus, lithium 2 plus is what you will have. So in the case of hydrogen, it's a neutral atom, but in the case of helium, that is a positive ion. And in the case of lithium also, it would be a positive ion. So in the case of helium, you remove one electron, and in the case of lithium, you remove 2 electrons to ensure that there is only one electron which is going around the nucleus. So that is how you ensure that there is only one force acting on this electron. So that is why whenever we talk about this derivation, we always talk about hydrogen or hydrogen-like atoms. Okay, so all it means is that you are going to have only one electron orbiting around the nucleus. Only then this derivation holds good. The moment you bring in more electrons, then this won't hold good, for the simple reason that this is not the only force acting on the electron. If you understand that, then we will proceed further. So F now is this. This is the force of attraction here, and assuming that this is going around this velocity. Okay, so it's going around this nucleus. So what do we know? So the electron is moving in this direction, and the force is acting towards the center of the atom, meaning that this force acts as the centripetal force. So there is a centripetal force, then I can equate this force to mv squared by r. So this force k z, now E is squared by r squared, is equal to m times the centripetal acceleration, which is nothing but v squared by r. So from this I can remove this one, and I can have two equations from here. Okay? So first of all I can find the radius, right? So if you want to find radius, then what would I have? I'll have k z e squared by m v squared. Okay? So k will become 4 pi epsilon naught, 1 by 4 pi epsilon naught, so that gives me 1 by 4 pi epsilon naught m v squared, and then z into e squared. Okay, or I can remove this and then say z e squared. So if I am going to talk about only hydrogen, then z becomes 1, then it will become, the whole equation will become e squared by 4 pi epsilon naught m v squared. That is for hydrogen. But this is the most general equation. Okay? It's going to be z e squared by 4 pi epsilon naught m v squared. Okay. Or I can find v. Okay. How do we find v? So v can be, I can bring m here. So that results in v square is equal to k z e squared by rm. So that's v square actually. So now so the v you're going to have. Okay, so these two things you can, these expressions you have. So r is k z e squared by v squared, v is k z e squared, root of k z e squared by r times the mass of the atom. Okay, and again if I do this, expand, I can substitute the value for k, which is simply 1 by 4 pi epsilon naught. So I get z e squared by 4 pi epsilon naught r m square root. Okay, so this is one. So notice that if you want to find r, then I should know v, or if you want to find v, then I should know r. So without knowing either r or v, I cannot find the other. So that is the limitation of this. If you know, I should know at least the radius of the atom to find the velocity of the speed with which the electron is revolving around the nucleus. Or if you know the velocity, then I can find the radius. Then I need to find these two difficult quantities. Okay? So that is there. And from here, I can also talk about the energy of this, right? So what do we know? What's the potential energy of the electron here? So the potential energy U of the electron is going to be equal to, we know, kq1 minus kq1 q2 by r, right? So from your electrostatic lessons, you know that it's going to be minus, potential energy is simply k minus k q1 q2 by r. So that would be minus k, q1 is going to be z and then e, so e square by r. Okay, so that gives you minus z e square by 4 pi epsilon naught r. Okay, so it gives you this expression. And what about kinetic energy? So kinetic energy is simply, let us call it as Ke simply half mv square. But from here mv square is equal to kz e squared by r. So that would be z e squared. I'm going to expand k, which is 4 pi epsilon naught into 2. So that will give you 8 pi epsilon naught to r. So this is u, this is k, and total energy E is equal to u plus ke. So that would be equal to, if I add these to this minus z square by 4 pi epsilon naught r, then z square by 8 pi epsilon naught r. When I add them, then I will be left with minus z e square by 8 pi epsilon naught r. Okay, so this is the energy consideration. This is general. This is general for all the hydrogen-like atoms. And if you need to do it exactly for hydrogen, then Z will become 1. Then all other things will fall in place. That's it. And Z will become 1 in this equation, that equation. On all the 4 equations, Z will become 1. So you are done with it. Okay. So this is your Rutherford atom model. Now, we have to talk about Bohr's atom model. Okay, Bohr's atom model actually simplifies this equation. That's the beauty of it. In Bohr's atom, the moment you talk about Bohr's atom model, you don't have to worry about what the velocity is or what the radius of the atom is. They can be calculated very easily from other quantities, the other known quantities. How do you do that? It has to do with the second postulate of Bohr's atom model. First of all, let's talk about the Bohr's atom model. The Bohr's atom model has 3 postulates. So what does he say? The first postulate removes the problem with Rutherford's atom model. What is the problem first? The problem with the Rutherford's atom model is this. We say that this electron is going around the nucleus. So the electron is actually accelerated now, right? Without the acceleration, it cannot change its direction. So there is an acceleration. But what do we know? The accelerated electron will emit electromagnetic waves. That is from your electromagnetic waves lesson. So when you accelerate, we say that constant current will not produce electromagnetic waves. We also say a stationary electron will not produce, stationary charge will not produce electromagnetic waves. But we said that if a charge is accelerated, meaning that the magnetic field produced by this charge, because accelerated charge is current, a varying current now, okay. So the current will produce magnetic field. Because the current is varying, then you will find varying magnetic field. And the varying magnetic field will produce an electric field. And if that is also varying, then that will produce magnetic field. So all these two things will keep, aiding each other. So you will have a wave effect there. So the accelerated charge will produce electromagnetic radiation. So then, which means that it's spending energy, it is sending energy, it's spending and sending energy in all directions. So once you keep losing energy this way, then what happens is that the charge will spiral. It will keep losing energy. It will fall into the nucleus. So if it falls into the nucleus, then no atom can exist. But then atoms do exist in the universe, and without atoms, you and I cannot be present. The fact that you and I are here talking about it tells you that the atom is stable, meaning that the electron does not fall into the nucleus as predicted by Rutherford's model. Okay. So Bohr's first postulate tells you this. It says this: the electrons are stable. The electrons do not radiate energy when they are circling the nucleus in stable orbits. He calls them as the stable orbits. Okay. There are certain orbits around the nucleus, and if you find an electron in those orbits, the electron will go around this nucleus, but it will not propagate electromagnetic waves. It will not lose energy. So that is the first postulate. And then the second postulate is the most important postulate. That postulate tells you how to identify those stable orbits. Okay. He says only in these stable orbits no electromagnetic radiation will take place. But in all the other orbits between these orbits, then if the electron tries to occupy any of the other places between these orbits, then it will start radiating energy. Okay, which means that it leads to the question, how do you identify these stable orbits? I mean, is it at 1 centimeter, is it at 2 centimeters, is it at 3 centimeters from there, or it is at 1 picometer from the nucleus, or 3 picometers? So you have questions like this. How do you identify those orbits? Then he says this. In those orbits, in those stable orbits, the angular momentum is an integral multiple of h by 2 pi. So he says, in those stable orbits, if you take the first stable orbit for an electron, then the angular momentum will be h by 2 pi. And if you take the second stable orbit for the electron, it will be 2h by 2 pi. The third stable orbit will have 3h by 3 pi. So this is the angular momentum of the electrons will be different in these orbits, and they are given by this expression, which is angular momentum L is equal to mh by 2 pi. And once you get this, then these equations will become much simpler. Okay. And the third postulate is this. Okay, so in these orbits where you have the angular momentum is equal to mh by 2 pi, the electron will be stable, it will not radiate any energy. But at all other places, all other orbits, if it tries to occupy there, then it will start radiating energy, and it will fall back to one of the stable orbits. That is the third postulate. So the first postulate says that there are certain orbits around the nucleus which are stable. If the electron is in those orbits, then it will not radiate energy first. And the second postulate is how to identify these orbits. It says in those orbits, the angular momentum is going to be an integral multiple of h by 2 pi, where h is the Planck's constant. So L is equal to nh by 2 pi. N is an integer. So that's the second postulate. That is how you identify the stable orbits. First postulate talks about stable orbits. Second postulate tells you how to identify those stable orbits. And then the third postulate tells you what happens when the electron does not occupy one of these stable orbits. When it tries to go to other orbits which are not stable, then what happens? What happens is that energy will be dissipated. Okay, and it will be radiated from, the energy will be radiated from the electrons. The electrons are not stable there. So it can go from one stable orbit. So when you give it energy, it can go from a lower stable orbit to a higher stable orbit. And when it jumps from the higher stable orbit to the lower stable orbit, then energy will be radiated from there. So those are the three postulates. Okay. With that in mind, let us see how the second postulate helps you simplify this derivation. Let's see how Bohr's second postulate simplifies these equations. Okay, what does the second postulate say? This is the second postulate. It says that the angular momentum of the electron in the stable orbit is equal to nh by 2 pi. right? So the angular momentum L is equal, okay, I'm using capital L is equal to nh by 2 pi. It's a magnitude. It's a magnitude of the angular momentum. But what is angular momentum? So angular momentum is actually equal to r cross p. R cross p, which is equal to r p sine theta, and then the unit vector in the perpendicular direction to both these vectors. Okay, so that is rp sine theta. So if you just take the magnitude alone, then you will get this, right? What is the magnitude of this? That is equal to rp sine theta. So what is p? It is mv. It's linear momentum. So you get m r v. And what about sine theta? If the electron is revolving around the nucleus in a circular orbit, then r and v will be perpendicular to each other. So sine theta will be 1. Theta is 90. So mrv sine 90. So you get this. It's circular, then L is equal to mrv. Okay. Now I can equate these two, right? I can equate these two. So L is equal to nh by 2 pi. This is my equation 1 and this is my equation 2. So these two are equal. So I'll say m or v is equal to nh by 2 pi, where r is the radius of the nth orbit, right? Let's say radius of the nth orbit, and then Vn is the velocity or the speed of the electron in the nth orbit. Okay, so how do you find V from? So Vn, the speed written as nh by 2 pi into Rn m. Okay, so this is what I get here. Okay, now Vn is this. I can take this value and substitute that here, right? Because V is equal to Z squared by 4 pi epsilon naught into Rm. So I can take this. Okay, Rm can be written as nh by 2 pi into Vn. So I can switch it, right? Okay, I'll do it. I'll switch this here. So this is going to be R and M is equal to 2 pi Vn. Okay. So what I get here? If I substitute that here, so V or a Vn is equal to Z and then E squared by 4 pi epsilon naught into nh by 2 pi to Vn square root. So that gives you pi and pi will cancel, and then 2 will cancel with this 2. So this goes up, so that gives you Vn Z E squared by 2 here epsilon naught n h square root. Okay, so if I square both sides, then what would I get? I'll get Vn square equals Vn Z E square by 2 epsilon naught n h. Then this and this can cancel, then simply Vn is equal to Z E square by 2 epsilon naught n h. Okay, so this is for a hydrogen-like atom. So this is a general equation. If I have to do it for just hydrogen, then Z will become 1. So I simply get E squared by 2 epsilon naught NH. And if you want to do it for the first stable orbit, then this N also will become 1. So I'll simply have, which I'll call as unexcited state, right? V naught. Unexcited state will get, this will become 1, this will become 1. So then I'll have E squared by 2 epsilon naught H. So we know this. We know the charge. This is a constant E, 1.6 10 to the power minus 19, the whole square. 2 is a constant. Epsilon naught, 8.854 to 10 to the power minus 12. And then H, 6.6 10 to the power minus 34. Then if you put these things together, then we know the speed of the electron in the unexcited orbit of the hydrogen atom. So this is the hydrogen atom. This is a general expression for hydrogen-like atoms. Okay. So this is general expression, and this is for hydrogen alone. Okay, because we've made Z as 1 and N as 1 again, and this is what you get. Okay, so once you get this, then you can find the radius, right? Finding the radius becomes easy now. What do you do? So radius is this, Z squared 4 pi epsilon naught M V squared. So you got V here. So you can find radius. So what is your radius of nth orbit is going to look like? Rn is equal to Z E squared by 4 pi epsilon naught M to Vn square, right? Nth orbit. So that gives you this. So Z E square divided by 4 pi epsilon naught M. Vn is equal to Z E square by 2 epsilon naught NH the whole square. Okay. So what's going to be Rn now? Rn is going to be equal to, take this part up. So Z E squared into, this will become 4 epsilon naught squared N square H square is divided by 4 pi epsilon naught M Z square e to the power 4, because we're squaring this term also. So this is what you get here. Now start simplifying. Z will go, and we'll get Z here. E squared will go, we'll get E squared here. 4 will go, 4 also go here. Epsilon naught will go, epsilon go there. So that's all we get. So that results in Rn is equal, this is gone, this is gone, this is gone. You get N squared H squared epsilon naught, so divided by pi Z M E squared. So this is the radius of the nth orbit for a hydrogen-like atom. Okay, so this is the speed of the electron in the nth orbit, and this is the radius of that orbit. So you can very easily find these two things. Okay, so notice here that this is not expressed in terms of R here. Now we are expressing V in terms of all the constants. Again, you are expressing R in terms of all the constants that you know. So you don't have to measure anything, but you can find the value of these things without measuring them. Okay, now this is for hydrogen-like atom. So if you need to find the radius of hydrogen in the unexcited state where n is equal to 1, when the electron is not excited. So then what you get here? So this would be, this n will be 1 for hydrogen. For hydrogen, and say this, I think call this as R naught, right? We call it as R naught, I suppose. For hydrogen, R naught is equal to, n is actually 1, okay? N is 1. So h square epsilon naught divided by pi, say Z is 1, atomic number of hydrogen is 1, m is squared. So you get pi m e squared. So now you can easily calculate the radius of the first orbit, or the unexcited orbit of hydrogen in this. Okay, so this is called as a Bohr radius actually. If I put these numbers, then it gives me 5.29 at 10 power minus 11 meters. So this is actually equal to, this R naught is actually equal to 5.29 to 10 power minus 11 meters. So that's the radius of the unexcited electron in hydrogen. So if you excite it, if you give it energy, then it will go from that orbit to another orbit, a longer orbit. So then the radius of the hydrogen atom will change in that case. But this is the radius of the unexcited atom. Okay. You notice that this radius is directly proportional to n squared. Okay, so the radius of the second orbit would be 4 times the radius of the first orbit, and then the radius of the third orbit would be 9 times the radius of the first orbit. So that you can figure out here. And also we can see that this radius is inversely proportional to the atomic number. Of course, then the mass also will change, but you can see that. Okay, so the greater the atomic number, then the smaller the radius would be. This. Okay. That's because of this inverse relationship. So if you take helium, if you remove the electron, one electron in helium, and you make it as hydrogen-like atom, then the radius of that orbit, the first orbit, the unexcited orbit for that helium ion now, will be half of the radius of hydrogen atom, because Z is 2 there. Okay. And for lithium it will be 1, even less than that actually, because like the mass will be 4 times that, right? So the mass is 4 times. This is Z is twice, so 8. So it will be 1/8 of the radius of hydrogen for helium ion. Okay, so you take hydrogen like helium, which is helium ion, and in the first unexcited state, the radius of it is going to be 1/8 of the radius of hydrogen atom in the unexcited state. Okay, we can also do the energy calculation. You know that E is equal to minus E squared by 8 pi epsilon naught R. So I can do that too. I'm going to make use of, since I've done this, I don't need this part. So, E is this energy is minus E squared 8 pi epsilon naught R. So E is equal to minus Z is total energy minus Z squared by 8 pi epsilon naught R. But you know Rn is this expression, so I can substitute this there and find E. E is going to be equal to minus Z E squared by 8 pi epsilon naught into for R. I'm going to have Rn, so let's say Rn. So N squared, then H squared epsilon naught divided by pi Z M E squared, and take it up. That will be pi Z M E squared. So this is what it's going to be. So this pi and pi will be gone. So what would it be left with? This E is now going to be equal to minus m into z square e to the power 4 divided by 8 n square h square epsilon naught square. Okay. So that's the energy, the total energy of the nth orbit. This is for hydrogen-like atoms. For hydrogen, Z will become 1, and if you're talking about the unexcited state, then N will become 1, then you can calculate it. Okay, so E naught, I'll say, or E1, whatever you want to call it. So to minus m e to the power 4, so divided by 8 h square epsilon naught square. So if I just put in these numbers, then I'll get 13.6 electron volt. Okay, we convert that into in joules. Okay, for hydrogen, for joules, this would be 2 minus 2.18 into 10 power minus 18. Minus 2.18 into 10 power minus 18 joules, or this is also equal to minus 13.6 electron volt after dividing that by 1.6 into 10 power minus 19. So you get this. So this is for the E naught, or the E1. Yes, it's for the first one. Then the second one, third one, fourth one. It's going to be, because you can see that this has an inverse relationship with n squared. So then you take it and divide that by 4, 9, 16, 25 and so on. Then you will get the energy, those levels. The energy is actually increasing because it's a negative number. You notice the total energy here, you found that to be a negative number. So the smaller the number, the bigger it is. So as you go further from the nucleus, then the energy of the electron increases. So when you give electron energy, it will go further from the nucleus. Okay, if it is here, and it will go here, then it will go here, go here. When you keep giving energy, then the moment you give plus 13.6 electron volt, then it will go out of the influence of the nucleus. That is for hydrogen. But this is the general equation for all hydrogen-like atoms. I keep talking about it. Hydrogen-like. It's not true for all atoms, because all atoms you have other electrons too. So this expression cannot be used. Okay, this can be used only for hydrogen-like things, meaning there is only one electron orbiting around the nucleus. All the other electrons have to be removed or ionized. Only then can you use these expressions. So you have one equation for the velocity of a hydrogen-like atom, and one equation for the radius of the hydrogen-like atom, and then one equation for the energy of the hydrogen-like atom. Okay, so I hope this is clear to you.